kinetic. Oh, sorry, let me close this one.
We have no homework in this chapter. Thank God. This is only one chapter.
You're so weak. I give you a few questions to do over the weekend.
No, but they are
And you're
hard.
falling apart.
No.
Right. Kinetic and potential energy. So which one was kinetic? What type of energy is kinetic? Moving. And potential?
Which is going to do.
Like future. Yeah.
You want to learn them in Arabic?
No, thanks. You're okay. Thank you. Did you write these down? Kinetic and potential energy.
They sound nice.
Go on, what's kinetic?
حركية potential كامل.
Kinetic is hakia,
حركية.
haki,
Yeah.
and potential.
كامل. بطل كامل وبطل حركية.
Haki and camera.
كامينة.
Kamina.
كامل.
Kamin.
Yeah, كامل.
I've already forgotten. Right. Kinetic and potential energy. So we'll get a start on this. Okay, if an object is moving, then it has kinetic energy. This is what we mean. This energy is from some work being done on the object. That is, kinetic energy equals work done to give that energy. So, I'll explain now what I mean. So, let's say this has no energy, okay? And then, if it starts moving, it has energy. Where did this energy come from? From me.
Yes.
So the work I do gives this energy. So the energy it has is from me, from the work I do. Okay? So if I want to make something here, this is not moving, and now it is moving, let's say with V. Where did this energy come from, this kinetic energy? It must have came from somebody like me who pushed it. So I'll just write Ke for kinetic energy. This kinetic energy here equals the work I did to push it. Okay? So let's calculate how much work I did. If I know how much work I did, then I can know how much kinetic energy it has. So what's the formula for work? F multiplied by distance. Now, do we know the F? No. Do we know the distance? No. Okay, but we can use Newton's law. What does Newton say F equals?
F equals ma.
ma, and now we still have the S here. Yeah? Okay, now do I know the A? No. Do I know the S?
No.
No. So we'll have to do some information here. U, V, A, T, S. Well, I know the U is 0. I know the V is V at the end. I don't know the A. I don't know the T. And I don't know the S.
The A is 9.8.
No, this is pushed. We don't know the A.
Isn't V1?
The huh?
The V.
I don't know what the V is. I just called it V.
We are supposed to.
Yeah, I just said it's V. Okay.
Yeah.
So I'll just give you a minute to write this much down. It's a little proof I'm doing here. So if you could just write this down, and then I'll continue.
We can solve it.
Yeah.
This root UV which
Equations of motion. Okay, you have this much?
Yes.
Now we know V squared equals U squared plus 2AS. But what does U equal? 0. So V squared equals 2AS. So what does AS equal? A half
half
V squared. So if I put that in here,
half mv squared.
yeah, I get a half mv squared. That's the work that I did, which should equal
Kinetic energy.
kinetic energy. So we have our first formula. The kinetic energy is equal to a half mv squared. I'll zoom out. Is that okay? Have you seen that formula before?
This one,
Yeah, I'm sure you have. Have you seen where it came from?
Yeah.
from the kinetic
You
energy.
saw this proof
Yeah.
before?
Like there are many ways to do it. We can find it with another formula. The one
Maybe.
S is equal to half mv squared.
I suppose.
This come in the exam.
No.
This is the formula.
Just the formula, yeah. Okay. You got that? Continue? Is that a yes?
Yes.
Yeah. Okay. Now, the next one is potential energy. So anyways, just before we continue, just a very quick example of how this works. So for example, if I have my man here and he's running and his speed is 10 meters per second and its mass is 100 kilograms, then his energy, his kinetic energy, is a half mv squared, which would be, let me see, 50 times 10 squared, which is 5000. So that's, 5,000 joules.
Why it's 50 multiply?
A half m.
Oh.
Half m. As a simple example. Yep. Okay, next now, continue. So, here, let's say this is a ball, and its mass is m, and its height is h. So, here, when it hits the ground, it's moving. Yes, of course it is. So it has kinetic energy. Where did this energy come from?
Move from the potential.
Yeah, it must have had potential energy up here, and this potential energy turned into kinetic energy. So we want to know what's the formula for the potential energy at the top. So we can say, if I take down as positive, yeah, we can say V squared equals U squared plus 2AS. And again, it starts at rest. So what's the U? 0. So I get V squared equals 2AS. I'll multiply by a half, so I get a half V squared equals 2AS. Thank you. Half V squared equals AS. I'll multiply both. Oh, we know what the S is. What's the S?
S is the H.
Yeah, we actually know the A and the S. So the A is G and the S is H. I'll multiply both sides by M. So I get a half mv squared equals mgh. But this is kinetic energy. And this kinetic energy here equals this potential energy here, because this became that. So that means then we have this formula, potential energy equals mgh. And maybe this is another formula you remember from high school. So this is our second one. If you can write this down, please.
Also, kinetic energy is mgh.
Well, not quite. This is just part of the proof. In this example it was, but this is the result I want.
Kinetic energy is equal to potential energy.
In some situations, yeah. In this situation it does, of course.
But it's not K equal MGH is not formula, because it's equal.
It is for this exact problem, and in a lot of examples we will do, it will be true, but not in every question. So I wanted to prove these formulas. Maybe you've seen the proofs before, maybe not in high school, I don't know. Do you think you've seen this proof?
Yeah, but PE is different.
Different? What's different? Is this the same? I hope this is the same.
Yeah, it's the same, but PE is different.
Oh, okay, what do you use for, not PE? I'll give you some letters that people use. Sometimes people use a V or a U.
U, yeah.
Okay,
yeah.
alright. Oh, sorry, yeah, U, yeah. I use KE and PE, but some physics books use a T. No, sorry. Some books use a T for this one or a V for this one. Some books use a U for this one or a V for this one. You think you use T and U? Okay.
I use the same.
T and U?
No.
KEPE? Yeah.
Why both V?
Huh?
Why both V?
I prefer KE and PE. Kinetic energy, potential energy. It's a bit clearer. Okay. Continue. Yeah? Okay, so let me just see what's next. Okay. Now, there's a couple of things, and then I think I'd like to do one example, and then we can continue this next time. Okay? Yeah. Oh, sorry. You don't have. Do you need to write this down?
No, I will.
Watch the video.
Yeah.
Great. And then you can hear yourself saying, "I will watch the video." Okay. Right. Now, a little bit about potential energy. So, let's do a very simple example. Here is my cup of coffee, and let's say the height here is 2 meters, and let's say the mass is 0.1 kilograms. So how much potential energy does it have? M, G, and H, whatever that is. That would be 0.981 times 2, which is about 2 joules of energy. What's that? About 1.96 joules. So if I hold this up here at 2 meters, it has nearly 2 joules of energy. So if I let go, the energy will change from potential to kinetic. Yeah, as it falls. Okay. I'm going to say this, and then I'm going to say this, and then you're going to forget it. Then I'll say it again later in the course, and you'll forget it again. And then I'll probably say it one more time, and then maybe you'll remember. It'll be much easier if you just remember it now.
Okay.
Okay? And you're thinking, yeah, I'll remember it, but then next semester it'll be... Okay, so just try to remember this now. It'll make things easier.
Okay, I will write it in the notebook so I cannot forget.
Yeah, okay. So look, you have, let me try and draw this here. 1, and then this one, and then this one here. So we have okay, so there's 3 situations here. In the first situation, the H is positive.
Yes.
Here the H is 0, and here the H is negative, which also matches with the 3 situations. Here potential energy is positive, here potential energy is 0, and therefore here potential energy is negative. Now, the point I'm making is this. If the potential energy is positive, then it has energy.
Yes.
It can do work.
Yeah.
Here, if the potential energy is zero,
No work.
Constant.
no, we call this free. It means it can't do work. It can't do anything. It's just free. It's just there. It doesn't do anything. Okay. And then the last one, when potential energy is negative, how would we describe him? Describe him. Is he free?
No.
He's not dead. No. Is he free? No.
That is down.
Does he have energy?
No.
Well, not really. We say that he's trapped, meaning if he wants to be free, we must give him energy. Now, this is a lot like with what you've done in chemistry. When the electron is on the atom, it's trapped. If you want to take the electron away, you have to give it energy. Okay? So if the potential energy is negative, we say it's trapped. It needs energy to be free. Okay? So I summarize that here in these bullet points. If the potential energy is positive, then it has potential energy. If it's zero, then it's called free. And then if it's negative, then it's trapped. Or we also say it's in a potential well. Yeah. And I drew my example already. So please note this. You can draw the picture if you want as well, okay? But this is the key. Now, it took me a while to remember this also. And I think the reason it took me so long to remember this, and maybe the same reason it takes you so long to remember this, is because we often think that energy can't be negative. But energy can be negative in this example. Potential energy means it's trapped if it's negative. Yeah. So potential energy can be negative. If it's negative, it just means that it's trapped. Okay.
No value. No value.
No, just negative value. So, for example, in my picture, if here the potential energy was equal to minus 10 joules, then that means, 10 joules would need to be given to the man to be free. He would need to do work of 10 joules.
And 10 joules to just be there.
Well, he needs 10 joules to get out, to be free.
He needs energy. When it's negative, he needs energy.
He needs it, yeah.
When he's positive, he's having his own energy.
He can do work, yeah. So here, he can do work. In this case, the work he could do might be to kill someone underneath him when he falls on them. In this here, he cannot do work, but he doesn't need any energy, so he's free. And this one here, he would need energy to be free. Work would need to be done. Okay? Yeah? Alright. So, let me see. So the conservation of energy implies that the initial energy of an object equal the final energy. So, I suppose I will just finish with maybe this. Let's say you have some story, I don't know, the guy is skiing. Yeah, you like my pictures, I know it.
But it should.
He's skiing. Snow. You know?
Yeah.
Yes, snow, yeah. So, here, let's say he's going at, 2 meters per second, and here
Yeah, alright.
Hang on. There he is, speeding at the end. Let's say it's 10 meters per second. So here he has energy. What energy does he have? He has two types of energy. He has firstly kinetic energy because he's moving, and then secondly, because there's a height, he has potential energy. And let me just zoom out a little bit here, and let's just say that's not quite the end of the story. It goes down further. Now here, let's look at the man here. What type of energy does he have? He has kinetic energy, and actually he also has still some potential energy. But remember, we said energy can only change, so it means that the energy here is the same as the energy here. Or, in other words, the kinetic and the potential at the start equals the kinetic and the potential at the end. So this is what we mean by conservation of mechanical energy. The energy at the start equals the energy at the end, or in other words, the kinetic plus potential at the start equals kinetic plus potential at the end. This is a very useful formula. Wait, Mayor. Be patient. Okay, did you write this down? Yeah. Okay. So I think what's next. Sorry, Andy, do you have this?
Yeah.
Yeah. See. Let me just check how many lessons I have left for mechanics. Now these lessons, that's 1, 2, 3, 4, 5, 6, 7, 8. Okay, I think we'll just about be okay. Let me just think. I'll have to continue this next time, but because there won't be any homework, I'll definitely get this one finished as well. And then on Friday, what's this one? Okay. Oh yeah, collisions. That's okay. Yeah, it'll be a little bit tight, but we should be able to finish it. These two topics, if you've studied them before, you know that they're quite difficult and big. The circular motion and the simple harmonic motion. So these will be double lessons. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay. I think we'll be okay. We'll be just about okay. Right. So what I was thinking is, because you don't have any homework to keep you busy, I'm going to give you a small test next time. That's right.
What?
Next time I'll give you a test in class.
Next lecture?
Next class. Yeah.
Which,
Wednesday.
all of it?
Next class.
All of what you studied from the beginning?
It's a good thing you don't have homework, so you can study.
We can have homework.
Yes,
Yeah.
so we cannot
True.
have a test.
No,
You can give this homework. We can.
no, that's okay. It's okay.